Hi, welcome to Kernel and Cloud. In this video, we are going to understand Dijkstra's algorithm, one of the most important algorithms for finding shortest paths in graphs. If you are a computer science student or a developer, you have probably seen shortest path problems in class or in competitive programming, and if you have never come across it, you are at the right place. Today, I will explain what problem Dijkstra solves, and then we will walk through it step by step on a small example. Let's start with a practical picture. Imagine this is a map of your city. Here each of these are places: your home, friend's house, office, station, mall. Each road between the two places has a number on it. That is time it usually takes to travel that road in minutes. So from home to your friend's house it will take you 2 minutes, from your friend's house to station it will take you 4 minutes, and so on. Now suppose you are at home and you want to go to the mall. For that, there are many possible routes. You can go from home to office to mall, then home to friend's house to office and then to the mall. And then you can also go from home to friend's house, then station and then to the mall. There is also a route via the factory, so you can go from home to factory to office and then to the mall. Each route here has a total travel time. You just need to add the numbers on the roads you use. So from home to office to mall, it will take you 6 plus 2, 8 minutes, and so on. The question here is though, out of all these routes, which route is the fastest overall? So we are not asking which path has the fewest roads, we are asking which route has the smallest total time. And that's the fastest route from home to the mall. That exactly is what Dijkstra's algorithm tries to solve. It wants you to find the shortest route out of all the routes that are available without actually taking them. The shortest path idea shows up everywhere. We can see it in GPS apps like Google Maps, finding the quickest way from your location to a destination. In computer networks, finding the cheapest or fastest route for data packets between machines. Also in game AI, figuring out how a character should move from one point of the map to another efficiently. All of these are just the versions of the same problem. Given many possible routes with different costs, how do we find the cheapest one? So these are the real life pictures. To work with it using algorithms, we convert it into a more abstract form that computers handle well, a graph. Let's now formalize what we just saw with the home to mall example with a graph. Here I have drawn a graph version of the problem. Each circle A, B, C, D, E, and F is a node or vertex. Each line between them is an edge. The number on each edge is the weight, the cost, time, or distance to and from along that edge. Dijkstra's algorithm works on exactly this kind of graph input. Formally, the input is a non-negative weighted graph like this one and a start node S. In our example, that will be node A. And the output is the shortest distance from S to every other node in the graph. And we will also be able to reconstruct the actual shortest path. Like if we have to go from A to F, the shortest path could be A to C to D to F. So the question is, given this graph and a start node A, how can we systematically find the shortest distance to all other nodes without checking every possible path? Now let's run this algorithm step by step on this graph. Step 0 of this algorithm is to set up a table. In the table, we are going to mention all the nodes that we have to travel from A, including A itself. So A to A to B, A to C, up until F. For each node, we will store the current best known distance from A, so the shortest distance up until now that we have discovered from A, and the previous node on that best route. So if we are traveling from A to C to E, then the previous node for E would be C. At the very beginning, we have not explored anything. So distance to A is 0 and distance to every other node is infinity. That is, we have not determined them yet. And the previous node for all of them is blank. And that's how we will initialize the table. Now step 1. We start from our source node A. When we visit A, we look at all of the A's neighbors. The A's neighbors are B, C, and D. So we calculate their distances and add them in our table. Distance to B through A is 0 that is distance to A in the table, plus 4. So that's 4. So we add that in the table by replacing infinity, and the previous node in this case would be A. Distance to C is 0 plus 2, so that's 2. We add that in the table, and the previous node again is A. Now we are on the last neighbor of A, it's D. Distance to D similarly would be 6, 0 plus 6, 6. And then we are going to add that in the table, and the previous node will be A again. And with that, we are done with all the neighbors of A. We have traversed through B, C, and D. When we are done with all the neighbors, we can label A as a visited node. We mark A as green as it's a visited node. We look at the table. The numbers in table are now the first best known distances to B, C, and D from A. All the other nodes still have infinity because we haven't reached them yet. The main question now is, which node do we visit next? So we look at the table and we look for the shortest distance from A. The shortest distance from A now is C, 2, and that's an unvisited node. So we are just going to visit C next. We will repeat the steps. Let's check out the unvisited neighbors of C. C has two neighbors, D and E, and both are unvisited. Let's start from D. We are trying to see if the total distance from A to D via C is less than the distance in the table. Current distance to D in the table is 6. The new distance from A to D via C is distance to C, that is 2, plus distance to D, that's 3. So 2 plus 3 is 5. And in this case, since the new distance is less than the current distance, we should replace current distance in the table. So we will replace distance value with 5 and the previous node with C. And now that we are done with D, we will move on to E. Since in this case the current distance is undetermined, the new distance 6, that is A to C plus C to E, 2 plus 4, is smaller than infinity. We will replace the distance in the table with 6. Now that we have added the best known distances to D and E in the table, we can move on from C and flag it as visited. We will now visit the unvisited node with the shortest distance. In the table, the shortest distance to an unvisited node is B with distance 4. So let's visit B. In this step, B has only one unvisited neighbor, and that is D. The new distance to D is distance to B plus distance from B to D, and that is 4 plus 1 equals 5. Since the new distance is same as the old one, we are not going to change it. And as we can see that D was the only neighbor, we can now label B as visited. The next unvisited node with shortest distance in our table is D with the distance 5. So let's visit D. Now D here has only one unvisited neighbor, F. The new distance to F is distance value for D, that is 5 plus 2, so that's 7. So we are going to replace infinity with 7 here, and the previous node will become D. Since F was the only neighbor of D, we are done with F as well, and we can label it as visited. Now in the table, the next unvisited node with shortest distance is E, so let's just visit E. E here has only one neighbor, and that's F. The new distance to F is distance to E, that is 6, plus distance from E to F, and that's 3. So it's 6 plus 3, 9. Since the current distance 7 is smaller than the new distance, we will leave it as it is. And that's it about E. We can label it as visited now. The only node left now in this table is F, so let's just visit F. Since there is no more unvisited node left in the table, we have nowhere to go from F, so we will just label it as visited. Congratulations, we have marked all the nodes as visited. They are all marked green. And now this is the time where we stop the algorithm. And in the table, we have now the shortest distance from A to all other nodes in the graph. So if you want to go from A to C, the shortest distance is 2. If you want to go from A to E, the shortest distance is 6, and so on. Let's put this on test. Let's say we want to find the shortest path from A to F. We know that the shortest distance is 7 from the table, but what if we want to reconstruct the path as well? How do we exactly reach from A to F? And for that, we have to consult the table. We know that the shortest distance is 7, so we are going to go to that row and find the previous node. The previous node to F is D. So let's try this reverse path from F. So we are trying to reach F from D. If we go to D, we see that the previous node for D is C. So we add C to the path. And now we go to C. For C, the previous node is A. And now that we have reached A, let's reverse the whole path. We have A to C to D to F. So the shortest path to reach from A to F is via C and D. This also answers our home to mall problem. And that's it. This was Dijkstra's algorithm explained simply. Let me know if you have any comments in the comment section. And in the next video, I'm going to write this algorithm as code, and we are also going to discuss its complexity. So if you are ready for level 2, please watch that video. And do let me know if you would like me to discuss a specific topic.